By the way, I'm going to ask the audience if you can hear us on the other side of the void. Anyone can give me a sign?
Yes.
Thank you. All right. Welcome everyone to another Quantum Matter seminar. Thank you for joining us. It's my pleasure today to give you Stefan Kehrein from the University of Göttingen in Germany, who's passing by Boston on his way to the March meeting. He's been on sabbatical and take advantage of this opportunity to bring him here and share his work with us. So I've known Stefan for many years now. I think we met when you were in Munich.
Yeah, yes, exactly, yeah.
So, and before that, we were postdoc in Harvard, right here, but that was before my time in Boston. And you did your PhD, maybe you can remind me?
In Heidelberg, with Franz Wegner.
All right.
Yeah.
All right. So it's my pleasure to give you Stefan. Thank you for
yeah, so thank you for the invitation, and it's very nice to be here. It's also seeing Adrian and Greg, and we overlap back when we were a few years younger.
Yes, a few.
And so, so I like to describe myself as a condensed matter theorist with broad interests. And so this is one example where, at least I believe, and I'm trying to convince you, kind of, broad interests basically allow you to take certain ideas from one field and then see what kind of implications they have in a different field. And so specifically, what I'm going to present to you is basically like ideas and concepts from black hole physics lead to kind of understanding or predictions from, I think, our point of view, very unusual entanglement dynamics in quantum many-body systems. So this is what this title is about. And I should also add that this is probably the easiest calculation that I've done in the last 2 decades. But what is interesting here, in my opinion, is not the technical details of the calculation, but rather thinking about what the implications and the interpretation of this calculation are. So there's also a subtitle that I think all the you see, does this work? No, it doesn't seem to work. Okay, I have to do it by hand. Okay. So, okay, now how can I actually go forward? Okay, now I have to click here. Okay, the subtitle of this talk is why black holes are tidier than children, and I will explain that. To you at the end of the talk. So first of all, in terms of motivation, the problem with like capital P for all, at least for all parents, and that's the following. This is the state of the kids' room that you like. This is the state that you more typically have. And now, if I tell you that the kids' room is an isolated system, there are children in there, you just don't see them. And I ask you to basically say in which sequence these 2 photos were taken. It's pretty obvious that basically the arrow of time is this is first and then this comes afterwards. And actually, if you Google in the internet for like messy kids' room photo, what you find are all these like guidebooks that tell you how to go from here to here. So yeah, it's the other direction. But all of these involve bringing the parents into this closed system and somehow enticing the children to move from here to here without the parents losing their mind along the way. So the question that all physicists ask themselves is, how do we reconcile the second law of thermodynamics, or the error of time, with microscopic time reversal invariance if we look at this? Or kind of phrasing it in a kid-friendly term is, if you can take the thing out of the shelf, why can't you put it back in the shelf? Yeah? Okay, good. So, and now, okay, so this question, how to reconcile the second law of thermodynamics with kind of microscopic time reversal and variance. This is a question that goes back, of course, to the very beginning of statistical mechanics. So I'll use my laser pointer on the screen here. So unfortunately, the people soon can't share it, but I think from what I'm saying, it should be pretty obvious what I'm pointing at. So this is the H theorem by which Boltzmann basically derived using the Boltzmann equation for dilute gases, and it's called the H theorem because actually what he calculated is H, which is minus S, so he has the other sign because H is defined as the negative entropy. And basically he derived this inequality that the entropy of an isolated system is non-decreasing as a function of time. And now Loschmidt famously objected to this by saying that, well, if you basically reverse all the velocities, then the time evolution runs backwards, and then the entropy as a function of time must decrease. And or putting it otherwise, how can you derive an inequality like this if you know that the underlying equations of motion are time reversal symmetric? And so this is, this is well understood by now, and maybe a physics answer to this was already given by Boltzmann's reply to Loschmidt, at least that's attributed to him. Then try to do it, yeah, try to run it backwards, and kind of what he meant by this was explained very nicely by Thomson, which you actually know as Lord Kelvin. And he basically pointed out that, yes, let's use the following example. We have a gas that is initially confined in half the volume, and then we pull out the wall that is separating this volume in two parts. And then we will observe that the gas spreads out into the whole volume. So if we allow this to proceed for a certain time and then reverse all the velocities, yes, the system, the gas will return to basically occupying only half of the volume. But for large systems, or if you wait for long enough, even the slightest kind of error that you make will basically make it impossible to go back to that original state. Yeah? So this is basically yes, of course, you can find situations where the entropy is not going to increase, but is going to decrease, but it requires incredible fine-tuning. Yeah? Because in a way, there are much fewer microstates where you have all the gas molecules in only part of the volume, as opposed to them spreading out over the whole volume. So this is basically kind of what I'm showing right now. This is basically just a numerical simulation to exemplify this point. So this is these are particles in 2 dimensions. They are initialized with some random velocities, and they are interacting. And then one lets the system run up to a certain time, and at that time, one reverses all the velocities. And basically, what one would want to see is that the system returns to the original state. However, if you use floating point numerics, so these are the circles here, then what you will see is if you do the time reversal at a sufficiently short time, then yes, you do go back to the original state. So this is H, this is minus S. Basically the entropy decreases again to the initial value. However, if you do the time reversal operation at a later point in time, then what happens is that you do not go back. Basically, the errors have accumulated in spite of, basically because floating point numerics is not accurate enough, and you do not go back to the original state. If you do integer, basically integer arithmetics, so that's the line then of course you always go back because you don't make any rounding errors. So this now brings me to kind of the goal of this talk. So the goal of this talk is I'll show you a class of models where we will observe in kind of a non-equilibrium situation a decrease of the entanglement entropy, and actually a robust decrease of the entanglement entropy. So different from what we see here. Whereas the entanglement entropy will increase and then it will decrease again in a robust manner. And what is going to be responsible for this is the buildup of long range. One of the reasons why this is happening is the buildup of long range entanglement as a function of time.
So I just want to make sure I get your physical point.
Yeah.
Like if we don't do a computer simulation, but we consider a real gas and
Yeah.
actual container.
Yeah.
Say we put it all in the corner.
Yeah.
You know, we run time forward and
Yeah.
then we see it kind of diffuse out,
Yeah,
have
exactly.
constant density. But supposing we were going to try to run the time backwards.
Yes.
Then would you say that there were some kind of fluctuations in the
Yeah.
wall of the container
The
and that
system
would
is so
be the
chaotic.
noise?
Yeah, the system
that
is so chaotic.
Okay.
I mean, the slightest fluctuation will, if you wait long enough, will make it effectively impossible to go back. It's basically that just you will follow if you basically you will follow the trajectory that you want to follow for some time, but because the system is so chaotic, you'll start to deviate from this, and
That
then
in practice, this is because systems are never truly closed.
Yeah,
There's always
exactly.
some environmental
There's always some
fluctuation that's not
Yes, exactly.
time reversal invariant effectively.
Exactly. Yeah, there's always going to be some perturbation, or you won't be able to change to perfectly invert all the velocities, or you're going to shift the particle a bit. I mean, in theory, yes, it works, and it has to work, but in practice, it doesn't work.
Sorry, can I ask a question?
Yeah.
What if like the physical system is very dilute
Mhm.
and like there's no interaction and there's no collisions? Then like if we do the time reversal,
then the system would not be chaotic. Yeah, the system would not be chaotic, and yes, you would go back, and that would be pretty stable. Yeah, because then what you have done is an integrable system with just some ballistic motion, and then the errors are not going to grow exponentially if you have a small perturbation. Yes, you will pretty much go back. But that's, of course, that is a very, very special class of models. And the moment you take into account there is some weak interaction, that you basically that picture will become invalid at a certain point in time. Yeah. Okay. But so now this brings me to the kind of my outline. So I'll first tell you a bit about the entanglement entropy, what's the generic behavior, and compare that to the page curve, which is something that is known from black hole physics. After that, I'm going to introduce a model that we will see shows this page curve for the entanglement dynamics. I'll give you the results. All of that is pretty analytical. And one of the observations that we'll make is that the the state that we generate, basically while the entanglement entropy goes down again, that these states have some interesting properties. They are low energy variance states. After that, I'm going to generalize this. So I'm basically showing this for a very simple system because there I can calculate everything analytically, and I don't need to ask my students to help me with the numerics. But then I'll basically just show that this is actually completely general for a certain class of systems, except that you can't solve it analytically anymore. And then for details, I'll refer to this recent preprint. Okay. So now the generic behavior of the entanglement entropy after global quench in a quantum system, this has been explained by Calabrese and Cardi. And the picture is the following. So let's imagine we start in an initial product state that is completely unentangled. And we perturb the system, or this initial state is not an eigenstate of the Hamiltonian, then what happens is that from each point, let's say each point we start emitting entangled pairs of quasar particles, and here they assume ballistic motion. And if this entangled pair of quasar particle ends up in the different regions A and B, and I'm interested in the entanglement entropy with respect to this bipartitioning of the Hilbert space in these regions A and B, then this entangled pair ending up in the different regions leads to entanglement between the two different regions. And so one can see that if one allows for a longer time, basically until one measures the entanglement entropy, then we have more and more entangled pairs that end up in these two different regions. And for ballistic motion, this is a linear behavior. And this is, for example, for this x-axis spin chain. One can see this here. This is the linear growth of the entanglement entropy as a function of time. However, if you wait long enough, then at some point, the entanglement entropy is going to saturate. And that's basically because if you wait even longer, then the entangled pair is no longer going to be and end up with one partner in A and one partner in B. But in this picture, both partners would end up in region B, and therefore the entanglement entropy saturates. And that's basically what you see over here, the saturation. And the saturation value is proportional to the smaller of these two regions. Now, this kind of growth of the entanglement entropy with eventual saturation at a volume law, one finds this also in systems that are quite different from this. So, for example, in MBL systems, the main difference is that the entanglement growth is logarithmic. But even in systems where you have diffusive energy transport, so where you cannot, you don't have this ballistic propagation of quasar particles.
Sorry, I have a question. This seems like a very strong claim. So you're saying that if I make a quench, which, for example, could be projecting all of the spins in the A spin chain, in the A portion of the spin chain to a product state. And you're saying that if at that point I keep evolving it with the original CFT Hamiltonian, that the state of either A or B, let's say A without loss of generality, will be maximally mixed at saturation, because that's, or like very close to maximally mixed, because that's what it would have to be if the entanglement was volume law. I'd find that very surprising.
Well, I think essentially the statement is that the system is going to thermalize if you wait long enough. I mean, and if the system thermalizes, then you would expect this kind of volume law behavior for any subsystem of a thermalizing system. So I don't think this is surprising.
I mean, I don't think it's true if you use the Cardi-Calabrese formula for entanglement entropy, that the entanglement entropy for subsystems of thermal states, say at low temperature, are dominated by a volume law.
So I mean, for the Calabrese-Cardi models, of course, these are CFTs and they're not really thermalizing and so on. That's perfectly correct. I mean, you can calculate this and you find this kind of basically you find this behavior with the saturation at the volume law. I mean, for a generic quantum many-body system, you see the same kind of behavior, and you also see the saturation. And the unsaturation there I would understand from the thermalization of the system.
Sorry, I guess I just don't understand the organization of this slide then. On the left-hand side of the slide, you say generic behavior after a quench, you have some pictures, and then right under it, you specifically cite Cardi-Calabrese. So,
yes, exactly.
But then you're saying that CFTs are not generic. So
no,
what are you saying?
Yeah, CFTs are not generic in the sense that, that they will not truly thermalize. I mean, an integrable model, I mean, now, first of all, we need to kind of define what we mean by thermalization. If we look at local observables, I think in a CFT, you also observe thermalization, if I remember that correctly. But of course, these models are integrable in the sense that you have quasar particles with ballistic motion, and they are if there are any collisions of quasar particles in an integrable system, then the only thing that you have is a permutation of the velocities, so, or the rapidities. So that is very, very specific. That's a very specific class of systems. But even in these kind of systems, you will see the saturation at the volume law. And for more general systems where the only thing you can do is numerics, of course, it's not integrable, but you generically observe the same kind of behavior. I mean, numerically. I mean, even in these systems with diffusive energy transport. So this basically this gives you an idea of what happens in a certain class of non-generic systems, and it's easy to understand. It's easy to understand it in these kind of non-generic systems, but the behavior is much more general, which one can see numerically.
Yeah.
Okay. I'm happy to talk more about this later. Do you have any further question about this? Okay. So now there is one class of systems where one expects a very different kind of behavior of the entanglement entropy. So it's basically not this behavior where you have a linear increase or some increase up to a volume law, but the behavior where the entanglement entropy as a function of time will go down again. And these are black holes, and these pictures I've taken from a recent review. So let me just talk you through that. So what one sees here is basically this time diagram of a black hole. Basically this is the collapsing star, and this red line here is the event horizon. Now, at the event horizon, one has virtual particle pair production. This is the famous Hawking radiation, where one particle goes to infinity and can in principle be observed from the outside, and where the other pair of that particle, the other partner of that particle pair falls into the singularity. And in order for overall energy to be conserved, basically what this means is that the mass of the black hole becomes smaller as a function of time. So this Hawking radiation that is emanating from the black hole, this is black body radiation, the famous Hawking temperature. And over extremely long timescales, the black hole basically shrinks, and basically all its energy mass is basically carried away in the Hawking radiation, until eventually at some point the black hole has disappeared completely, and the only thing that is left is the Hawking radiation.
So, question here, just my ignorance of black holes. What is the microscopic mechanism that leads to the entangled photons?
Oh, this is semi-classical calculation from Hawking. So this is basically quantum field theory in curved spacetime.
Okay. So this is just mass.
Greg, let me try to answer that in a more specific way. So in normal flat space, you can have virtual particle pair production, and they're virtual particles, so they'll produce and they'll reannihilate, right? But you can imagine if you have what seems like virtual particle pair production, but one of them right close to the surface of the event or stretch horizon, then one of them will come out and the other one will go in. and then it's no longer a virtual particle pair prediction.
Mhm.
So then the virtual pair that's coming out of the stretch horizon should be interpreted as radiation coming from the black hole.
Another way of thinking about this is equivalent is to think of the Unruh effect. Yeah.
Okay.
Yeah. Okay. Okay. So the so let's now so where's the problem with this? Or where's the issue with this? This is essentially an argument that goes back to one page. So let's imagine, for simplicity, that our black hole is initially in a pure state, which means that if we assume that time evolution is unitary, this will remain a pure state. So the kind of the von Neumann entropy of this is always going to remain 0. Now, if we split up the total Hilbert space in the Hilbert space of black hole and the Hilbert space of the radiation, this means that if the overall state is a pure state, that the entanglement entropy of the black hole and the entanglement entropy of the radiation always need to be equal. Yep, that's basically, that just comes from the Schmidt decomposition of this pure state into this bipartite Hilbert space. Now, we know that the entanglement entropy is essentially bounded by the number of degrees of freedom that constitute, or the dimension of the smaller of these two Hilbert spaces. Yeah, if you have, for example, if you have a subsystem with 2 qubits, the maximum entanglement entropy that you can have is 2 log 2. It can't be larger than that. Now, if we, as a function of time now, plot the entanglement entropy, it doesn't matter whether it's the entanglement entropy of the black hole or the radiation, they have to be equal, then this calculation that I already mentioned by Hawking, basically quantum field theory in curved space-time, tells you that the entanglement entropy is going to increase initially linearly in time, which is basically just, again, this virtual particle pair production, or production of entangled particle pairs at the event horizon. When particle goes out, one particle falls in. It's very similar to this Calabrese-Cardi picture that I showed before. And again, you have this linear behavior. Now, however, one thing is different here, namely that the basically thermodynamic entropy of the black hole, or the number of degrees of freedom that we have in the black hole, decreases as a function of time because it starts to disappear. So at some point, and this basically, bounds the entanglement entropy. Yeah? The entanglement entropy cannot be larger, because if it were larger, this is basically like saying that we have an entanglement entropy that is larger than basically possible for the number of degrees of freedom that are available for the system, for the smaller of these two systems. And at some point in time, these two curves meet, and this is the page time. And so from unitarity time evolution, one then expects that the entanglement entropy has to bend down and go down again. And the issue with this is that this page time, this is approximately the time where the black hole has decayed to half its original mass. So at this time, the black hole is still, typical black hole will still be huge. And actually, the curvature at the event horizon basically is such that you assume that your semiclassical calculation is perfectly valid. We're very far away from Planck scales or anything where we don't understand the physics. Yeah. So the issue is that the semiclassical calculation gives you this continued increase of the entanglement entropy, but you know from unitarity of time evolution it must bend down. And this happens at the time scale where we believe that we understand all the laws of nature.
Can I ask a question?
Yeah.
So what fixes the beach time?
Sorry?
What fixes the beach time for a given black hole?
Basically, I mean, I would define it as the time where the entanglement entropy starts bending down again. Yeah, and it's basically approximately the time that these curves here, these two curves meet. And it's if you if one goes through the calculation, it's about the time that the black hole has decayed to half its original mass, which is still huge. Yeah.
But is there an expression for that in terms of the mass of the black hole? Like, say you're given that.
Yeah. Yes. Yeah. You can do that. So in a way, this is kind of, I mean, for condensed matter theories, at least the issue. So you have this problem at the time scale where you really don't expect to have a problem. And there have been countless resolution attempts to this unitarity of time evolution, because basically, kind of somewhere, basically something makes quantum mechanical time evolution non-unitary. There's tiny corrections, firewalls, more recently the island formula, and so on. So there's been this has been an ongoing debate in kind of black hole physics, trying to calculate this page curve. Yeah, or basically saying what is wrong with this calculation and why is something wrong at this time so early. And and now I first need to make a disclaimer. So I'm not going to even trying to contribute to this debate. Yeah. What I've been doing is I've been kind of taken this as a motivation to basically come up with a very conventional condensed matter system that shows the same kind of behavior. Yeah, namely an entanglement entropy that goes up and that goes down again, because this is different from what we typically expect and what we typically see in numerics. And as mentioned before, we will also see that kind of the states that we generate in this way have some unusual properties and some interesting interpretation. Okay, so this is the system that I want to now discuss in full detail. And so basically, it's really just a one-dimensional chain. I put fermions on this chain, and they can hop along this chain. For this here, I don't need any interactions. The first M laticides, that's my system. I don't want to call it the black hole because this is not really metal for a black hole, but this is the system. And initially, all of these laticides are full. And then here I have an environment that is much, much larger, and that's initially empty. And then the system and the environment, basically they are coupled by this hopping matrix element across the boundary. And the kind of the generic behavior that I'm interested in comes about when this coupling is smaller than the coupling along these two chains.
And are we supposed to think of that boundary as an event horizon?
Exactly. Yeah, that would be. Yeah, and that's exactly it. Because basically, if you now switch on the non-equilibrium dynamics, so basically, let's say you at time t equals 0, you prepare the system in this, in this product state. Here's also a trivial product state, it's a vacuum. And now at time t equals 0, you switch on this coupling across the boundary. Basically, what you can think of is that you have a particle going out and a hole going in. Yeah, and this is exactly this kind of entangled pair production at the boundary. So this is what one is mimicking with this. And this is going to generate entanglement. Yeah, and with respect to this bipartitioning of the Hilbert space. Okay. So obviously, similar to what I showed you before, a pure state remains a pure state. So the entanglement entropy of the environment or of the system part, they are always going to be equal, and I just call it the entanglement entropy. Now, why would one expect a page curve here? Well, it's really very straightforward. Obviously, what's going to happen is that all the particles from the system are going to empty into the environment. So the expectation value of the number of particles in the system is going to decrease as a function of time. So basically, it goes down to 0 if the environment is large enough. Now, if you ask the question, what is the dimension of the Hilbert space of this first M laticides if I know that there are exactly M of t particles in it? Well, that dimension is basically M over M of t. And that's how many possibilities you have. to distribute M of t fermions over M lattice. If you have M fermions, there's only one state. If you have no fermions, again, there's only one state. Basically, if this is the logarithm here for a sufficiently large M, and if the system is half full, you have the largest number of possible states. So if we think of this as a bound on the entanglement entropy as a function of time, then obviously the entanglement entropy can initially go up and then it can go down. But then it has to go down again because the system will empty. So basically, this is the very simple reason why you expect the page curve-like behavior for the entanglement entropy. And this simple argument is not quite rigorous, because what I'm doing here is that I'm neglecting fluctuations of the number of particles. Yeah, so I don't really have a fixed number of particles in the system. It's going to fluctuate. But fortunately for this very simple system, one can do the calculation in closed form and basically figure out the entanglement entropy as a function of time, either doing numerics for very large systems. So it's fairly easy to do this up to 10,000 lattice sites. Or on the next slide, I'm going to show you how one can also calculate this analytically in a certain way. So the numerical calculation basically builds on a formalism that's been introduced by Peschel and Eisler for bilinear Hamiltonians, which basically tells you how you can calculate the reduced density operator from the 2-point correlation functions, and the 2-point correlation functions you can easily calculate for the simple system.
Can I ask a question?
Yeah.
So if you perturb this bilinear Hamiltonian by adding some other terms, do you expect the page curve to be?
Yes, I'll come to this. This is topic generalizations. Yeah, this is generalization. So yes, you will, and for some cases we've already seen it, you see the same kind of thing. This is completely stable. Yeah? I'll explain this in a moment, but yeah. Let me do this first, because here it's completely unambiguous and you can calculate everything in closed form. But what you see here is really much more general. Okay.
I don't quite understand the motivation for why you have this Hamiltonian, which is moving particles out of your so-called black hole region into your, I guess, environment region, but you're not, as opposed to moving the dividing line, which separates the region that's identified as the black hole region versus the region that's identified as the system region. If I have a black hole, and that's the system that I'm trying to model, it's pack information. It's the densest way to pack information into a given space-time region at every, and your model expressly makes it not maximally densely packed.
Yeah. So as I said, I don't want to call it black hole. I call it my system. And I'm also not trying to model a black hole. I'm trying to kind of introduce a class of quantum any-body systems that show basically an entanglement behavior that looks like a page curve.
Yeah, but I guess my point is that I'm not sure that if that's all you're trying to do, that's all that difficult. I mean, like if we take for granted that one can model a black hole by a quantum circuit and ignore gravity and everything like that, then it's obvious that it follows a page curve. And one can find simple quantum circuit models like I did a few years ago, or other things that also exhibit a page curve. So I guess I'm not really sure why, like, I guess why this is surprising. Like these dynamics are very different from the dynamics of a CFT after a quench. Like there's no real parallel between those two.
Yeah. So again, if you listen to my introduction, that's what I said. I kind of use this as a motivation to come up with a class of quantum many-body systems that show this kind of behavior. I'm not trying to say anything about black holes, although I think there is a takeaway message about using a semi-classical calculation for calculating something like the entanglement entropy. Maybe you can bear with me for a moment until I go a bit further in my talk, because I think a number of the issues that you raise hopefully will become clearer. And I certainly have made no claims along the lines that you seem to think that I have. Okay. Okay. Now, a different way in which one can basically actually calculate this analytically is in the limit where we assume that the coupling between the system and the environment is weak. And the reason for this is that in this limit, well, you can always basically say that you can diagonalize the system. It's a simple finite chain, and you can introduce the corresponding single particle energies corresponding to the eigenmodes of that chain, and then these eigenmodes will be coupled to the environment modes. And so this is basically the picture here. These are the discrete single particle levels that are coupled to essentially a continuum of environment states. And if the tunneling is weak, then this coupling is essentially only going to couple to environment states that live in a small energy window around the single particle energy, which is given by the hybridization function here. And so, and now the main observation is that for the different single particle levels, these continuum states that I'm coupling to, they don't overlap. So essentially, I can think of this single particle level coupling to these states, this single particle level coupling to these states, and these are all disjoint environments, which basically means that I can split up this problem into capital M resonant level models that are coupled to disjoint environments. And for a resonant level model, it is very easy to write down the reduced density operator. The only thing that enters is basically the occupation of the mode that is decaying into the environment. And the system reduced density operator is just the product of all of them. It doesn't give you any immediate information about the spatial structure, but it reproduces the bipartitioning of the total Hilbert space and allows you to calculate the entanglement entropy analytically in the thermodynamic limit when you assume that the environment is much, much larger than the system. Okay, so now...
Sorry, is that last condition that m squared over n is...
M squared, yeah, let me just go back. M squared over n. So basically, you imagine you have m particles. You spread them out over the total of n plus m, so essentially m over n sides. So the density is m over n. And now you ask how many particles at that density will be in the system. That's m times m over n, just statistically. And if that number is very small, that means that the system empties out completely. That's basically where this comes from. Okay, now, so these are now some just numerical results that for typically 10,000 lattice sites. So here one can see that. So I divide the number of particles by the initial number of particles, or the number of lattice sites in the system, and I rescale the time again with the number of lattice sites in the system, and one can see that this, of course, decays as expected, and one can see that the entanglement entropy, so it's not exactly linear, it has log correction, it grows, and then, as expected, it starts to bend down again. And over here, this is now on a log scale. One can see this quite nicely. It goes up, and entanglement entropy goes down again. So what one can, this is now for different m's, with this kind of rescaling, all these curves fall on top of one another. And one can see that the kind of the page time, which I then define as the time where you have the peak, is proportional to m, to the number of lattice sites that we have initially. The entanglement entropy at that time is proportional to m. And if we look at a real physical observable, like the number of particles in the system, or let's say the current that goes across the boundary, which would be the time derivative of this, you see that nothing whatsoever is happening at the page time. Yeah? It just continues to decay. There's no physical observable, at least if one looks at the number of particles, that shows any unusual behavior at this time. What this also shows you is that you have this picture. This is the semiclassical picture that the particle current across the boundary is basically proportional to the entanglement generation. For each particle that crosses the boundary, basically in this picture that I showed initially, contributes to increasing the entanglement entropy. And we see that this picture obviously completely breaks down at this time. Yeah? The current just flows and flows and flows, but here the entanglement entropy starts to go down. It has to go down, of course. From the system point of view, this is not surprising at all. Now, kind of a nice way of plotting this is basically as a function of the fraction, how much the system has decayed into the environment. So here it hasn't decayed at all at 0, and here it has decayed completely. And this is now for different coupling strengths between the system and the environment. And this dashed line, this is this analytical model in the limit where g goes to 0. And one can see that one starts approaching this line pretty nicely. And over here, this is the same curve now for the purity. So the second Rayleigh entropy, and this is the Q to infinity Rayleigh entropy, so the min entropy. And all of them show the same behavior, especially here one can see very nicely it goes up. There's absolutely no indication of anything happening at later time, and then relatively sharply it starts going down again. So let's take a step back. And as I said, I think what in my opinion is interesting about this comes from thinking about this from the point of view of an observer in the environment. So from the system point of view, it's clear the system is emptying out, and the entanglement entropy at some point has to go down. But now imagine you are an observer who sits in the environment. And you have the system that keeps throwing stuff at you. It continues to keep throwing particles at you. And at some point, what is happening is that although you keep kind of receiving stuff, your entanglement entropy starts to go down. It's a bit like kind of sitting in that half of the cylinder, and you keep receiving things. And the entanglement entropy is going down. So it's kind of that you absorb more and more particles, but what is happening is that things rearrange themselves in such a way that actually the entanglement entropy becomes smaller. This looks as if you see a movie running backwards. All the more because this decrease of the entanglement entropy is completely robust. So if you start to perturb the system in a time-dependent manner, I think that kind of brings me to a question that was asked before, this is still going to happen. Yeah? Because as long as the system is going to empty, you must see this kind of behavior, which is easy to understand from the system. But if you're if you're the observer in the environment, it's not at all obvious that things are going to rearrange themselves in such a way that the entanglement entropy will go down again. Of course, it has to, because we have unitary time evolution. These two parts are tied together. But basically, if you're sitting in the environment, you would not understand this behavior if you did not have this information about what was going on, like in the long past where the system was initialized. And the other kind of message is that this semi-classical connection between the entanglement generation and the particle current, this obviously completely breaks down at a certain time, namely at the page time. Yeah, the current keeps flowing, but instead of the entanglement increasing, it actually starts decreasing.
Can I ask another question?
Yep.
So if we wait for a very long time, do we expect that there is a probability for particles to go back to the black hole again?
Yes, yes, and you see that in the numerics. You see that in the numerics. Actually, that's the main limitation for the time. Yeah, up to which I can run these numerical simulations, because at that largest time, you start having the first reflections from the boundary. I'll show you something about finite size effects in a moment, where you basically see where these reflections come and what they do. Yeah, so that's basically, that's kind of the limiting factor for the numerics. I mean, one can probably do this better, but there's no need to do that better. Yeah, exactly. Okay. Okay. And I should emphasize that, of course, this is basically, here we are talking about the entanglement entropy. We are not talking about the thermodynamic entropy. Yeah, so I'm not saying anything about the thermodynamic entropy decreasing or anything like that, because first we would need to define what we mean by thermodynamic entropy for this quantum system. So another property that that I think is kind of interesting about these states that one generates in the environment is that these states have a very low energy variance. So basically, the energy variance is basically this expectation value of the environment Hamiltonian minus its expectation value squared. And this essentially gives you information about how many eigenstates of the environment Hamiltonian my state is spread out. And the generic behavior, if you just inject m-independent particles into the environment, is that the variance is going to be proportional to m. Yeah? Each particle basically contributes a certain amount of energy variance, and the total energy variance is going to be proportional to this. With the state that is generated here in the environment, what one actually finds is that the energy variance of that state is independent of the number of particles. So it's only given by the coupling across the boundary. So it's much lower than what you have if you really inject independent particles, because these particles are not independent; they are generated by this unitary process. Well, the reason for that is again quite simply that the total energy variance of the total Hamiltonian is time invariant, and if you wait long enough, then the energy, all the particles are in the environment. So basically, the total energy variance is just the energy variance with respect to the environment Hamiltonian, and therefore this has to approach the value of the energy variance at time t equals 0. And at time t equals 0, the only contribution to the energy variance comes from this one term at the boundary. Yeah? So again, it's this picture, you're standing in the environment and someone throws particles at you, and the energy variance becomes smaller and smaller as a function of time, until basically it becomes of order 1 again. And this is again plotted here, and this dashed line is basically this is the result for an analytical model with the disjoint resonant level models.
So that result that it's the asymptotic variance is g squared. Is that because g is small, or is that non-perturbative? Like
no, this is not perturbative. This actually holds for, this would even hold for large g. This holds for all g. This holds for all g because it's really just, there's only one single matrix. So if you calculate basically delta h at time t equals 0, there's only one single matrix element that contributes, because in the system everything is full. Hopping processes don't do anything. There's no contribution. Environment is completely empty. There's nothing happening there. And you can only hop across the boundary and then back. And that's the only process that you have. So this is basically, in general, this would be, if you go away from one dimension, this would be kind of proportional to the size of the boundary and the hopping across the boundary squared. Okay, so now this brings me to this kind of question about the generalizations. So this behavior is, of course, completely general. Yeah, I showed it here for this model because one can analytically solve it easily, but it's completely universal. If you have, so basically if you have a bipartite Hilbert space and you have a pure state, then if effectively, so this is the Hilbert space of the system, and this basically this, if the colors get these regions here, basically they indicate how many states in the system do I need to represent my system state at a certain time. So initially here I assume it's a simple state, then I need more states in the system to represent it, and then here even more, and then but at some point I need fewer and fewer states because the effective dimension of the Hilbert space becomes smaller as a function of time. And so if I have, and because of this naturally bounds the entanglement entropy of the state that I'm generating in the environment and also the energy variance. So if I have some process that basically takes me into a small effective Hilbert space, whether it's a non-interacting model or an interacting model, essentially you're always going to see something like this. Yeah, it's as I said, it's not at all surprising from the system point of view, but if you're sitting in the environment, it is really not obvious what's happening there. And so, for example, this was a question: if you have a finite environment, and you have reflections from the boundary. So this is now the system has size 50, and here you have environments that are 75, 100, 200, and so on, lattice sites. Then you can see, and this is basically the behavior of the entanglement entropy as a function of time. Then you can see that if you have an environment that is just a tiny bit larger than the system, the entanglement entropy goes up, it kind of plateaus, and then it starts increasing again because you start having reflections from the boundary. And if the environment is twice as large as the system, then you already have a pretty robust decrease before you start having the reflections from the boundary. So basically, because people that do ultra-cold atomic gases, they're kind of curious if they can realize this. So this is an obvious question that they ask because their environment is going to be finite. And then, of course, also for interacting systems, you get the same kind of behavior. So this is now a Fermi-Hubbard model, still very small. This is kind of preliminary numerics. Again, coupled to basically to a free environment. And here, this is these lines here, they correspond to the number of particles that we have in the system. It's 2 lattice sites only with spins, so it's initially 4 particles. Of course, it again decays into the environment, and the entanglement entropy goes up and goes down. And then at this point in time, the system is not emptying out anymore because you start having reflections from the boundary. So basically, forget about this part. This is a finite size effect. But of course, you also see this for interacting systems. So this brings me to the summary. So I've looked at, these models have been introduced a long time ago, but I've looked at the system plus environment models in a slightly different way. They generate some non-equilibrium entanglement dynamics that is quite different from the entanglement dynamics that we typically see. It is easy to understand from the system point of view where this entanglement dynamics come from, but from the point of view of an observer in the environment, it is quite surprising what happens there. And it all comes about because of unitarity of time evolution in quantum mechanics. And this is a robust page curve. Even if you basically do some time-dependent perturbation, the system is always going to behave in this way. And basically what's responsible is in this model is that you build up some long-range entanglement. And at some point, if a particle after the page time leaves the system, it doesn't lead to more entanglement, but it kind of tracks entanglement across the boundary and starts to reduce the entanglement. One sees this complete breakdown of this semiclassical connection between particle current and entanglement generation. So semiclassics can be really completely misleading for a quantity as subtle as the entanglement. And in this manner, one can generate kind of interesting low energy variance states in the environment that have a much lower energy variance than what one would create by injecting independent particles into the environment. And this also brings me back to the question, why are black holes tinier than children? Because black holes tidy up the mess themselves. The entanglement entropy goes down, and with children this doesn't happen, or maybe on cosmological timescales that I've never observed.
Thank you so much for beautiful talk. We had a lot of questions in the talk, but maybe the audience wants to.
Maybe I have one more. So this last point, these low energy variance states. I mean, can you relate them to the entanglement entropy in any way, or?
I mean,
there's one example that I remember from Levitov. He was looking at like charge fluctuations at a point contact, and at least in some limits, you can relate like some of the fluctuations in the charge with entanglement entropy. So I don't know if there's something similar.
So it's not obvious to me that, I mean, of course, in a simple model, you can always find some connection because the model is simple, so you can make connections. But I'm not entirely sure that this would generalize to interacting systems. I mean, such a connection would generalize to interacting systems. So yeah, so I'm not entirely sure. I'm not entirely sure about that. Okay, yeah, I'm not entirely sure about that.
I have a question from the audience, Deepak.
Yes, hi. So I was very excited when I saw the title of this talk, and then I looked up your paper, and I read like the first 2 pages, and I was even more excited because I thought this is such a simple and such a beautiful picture that you're presenting. And I mean, even though Ning, who's in the audience, disagrees, but it is my personal opinion that this is the first time I think anybody has ever presented an exactly solvable many-body model which shows the page curve. Am I right?
So I mean, I've tried to do a fairly general literature survey, and I mean, I've not seen anything like this. I've also talked to people about this. I mean, of course, you, as was pointed out before, you can see a page curve if you shift the boundary. Yes, I mean, and there's a number of papers out about that in the literature. But from the point of view of the models that I'm generally interested in, and that, for example, you can create in ultra-cold atomic gases, the natural thing is to keep the boundary fixed. Yeah.
No, I mean, even with your model, I think one could probably modify it in such a way that the boundary does keep shifting over time,
Yeah,
and you would still get the same,
Yeah. Yes. All the more
Yeah.
you would. All the more.
Yeah. And I have a question. I mean, so again, I mean, I know that you put forth the disclaimer that you are not trying to describe black hole physics, but I mean, let's be honest. I mean, this is where the motivation comes from, right? To look at a model like this. So we should not be should not be afraid to ask if there are connections, right? So in particular, in recent years, there has been the island formula that has developed.
Mhm. Yeah.
And so I've tried to understand I mean, I've not been able to understand what this island is.
Mhm.
And I asked another colleague that, who does similar work. I asked him, like, do you have an understanding of this island in terms of exactly this kind of a system? So he
Yeah.
didn't. But so have you thought about that? Like, what would be the island in this?
So I haven't. So it's something that I would like to understand better. I'm not entirely sure if this is the right model for it, because I mean, the island formula essentially comes from a picture where you have a holographic calculation of entanglement entropies, for which you need a strongly interacting quantum field theory. At least I would argue that we need a strongly interacting quantum field theory. And the model that I'm looking at is not interacting. So I'm not sure if I would expect to see a connection here. But it's something. I mean, it's kind of on my. I have a question mark there. I don't know, but I'm not sure whether I would expect to find a connection.
Okay.
I mean,
Thanks so much.
I mean, but maybe one thing that came up in a discussion recently that I think is also kind of interesting is if you think about this low energy variance states, you could kind of ask the same question now for black holes. What is the energy variance that of your Hawking radiation? But then I think that the answer is going to be quite different from what I have in this model, because the horizon is proportional to the mass. So I think for a black hole, you actually don't have a low energy variance state in the same picture, in the same way that I have here. Yeah. So but anyway, so I'm not sure. I'm not sure about the connection with the island formula. I think the one thing that I do that is a bit a take-home message for me. I think from what people have told me about the island formula, it basically gives you necessary corrections to the calculation of the entanglement entropy, and that go beyond. Yeah, basically that go beyond the calculation that shows this linear increase without the downbending. And I think one thing that one can see here, or basically putting it a different way, the calculation of the entanglement entropy is tricky. Yeah, one needs to be very careful with it. And this is something that one can also see in this model here. Because this kind of naive semiclassical picture that looks so compelling, it really completely breaks down, because what happens is that somehow particles in the environment arrange themselves in such a way that the entanglement entropy goes down.
Well, I mean, anyways, I think it's really nice work. So thanks a lot for this talk.
Thanks.
Any other questions from the audience online? Please unmute yourself.
Yeah, could you go back to the slide where you first introduced the page curve? Not your page curve, but the actual page curve.
At the very beginning from the Almeri review, Almeri et al. Review.
Yeah.
In the meantime, I have a comment.
Yeah.
Okay, no, go ahead.
Yeah, okay, yes.
So to me, one major difference between what you're doing and this curve is that the yellow line for your curve would be horizontal. Because like the yellow line that sets the bound on the page curve comes from the log of the Hilbert space dimension.
Yes, yeah.
Because you're fixing the partition between your two sides, the theoretical Hilbert space dimension is constant. It doesn't change.
Well, not quite. I mean, so you can of course say this: the size of my system doesn't change, but the number of particles that effectively live in that Hilbert space. So the effective Hilbert space dimension that I have That does go down exactly in this way.
But the effective Hilbert space dimension, it seems like that wouldn't go down until the page.
Well, it goes up initially, and then it goes down.
I mean, I guess the thing that I'm saying is that black holes, even when they're going through page curve dynamics and things that are relevant to Page's theorem, even if you ignore black holes, the black hole system past the page time is maximally mixed.
Yes.
And
yes.
in your system, it's not really maximally mixed. You have to go through this. You have to go through this additional.
Yeah. So I can reach the page
an
limit.
effective Hilbert space dimension as opposed to the actual Hilbert space dimension.
So I should tell you, I can reach the page limit with my entanglement entropy by a slight modification of the model. So that's actually no problem. I can get the maximum allowed value. And I mean, I would say the maybe one difference is if I argue with the kind of the effective dimension of the Hilbert space is that effective dimension of the Hilbert space initially goes up and then it goes down. So it looks very similar to the entanglement entropy from beginning to end. Yeah, I mean, I think for talking about the thermodynamic entropy here, you would need to give me a definition how you want to define the thermodynamic entropy in the first place. And that is, of course, an observable dependent definition.
Sure, I mean, for black holes, it's dependent on the mass, but that's also dependent on the system size.
Yeah,
that's a key feature in black hole physics, and that's a feature that you're removing. You're removing the identification between the effective Hilbert space and the actual Hilbert space. And so I'm concerned that you're stating a result about not really Page's theorem, but a modification of Page's theorem where you replace Hilbert space dimension everywhere with effective Hilbert space dimension. And so it's actually not exactly the same result.
You guys should meet on Zoom.
Yeah,
I'm gonna put you in touch, guys.
Maybe that makes
I'm gonna send an email to the two of you with the Zoom link.
I think that makes more sense. Yeah.
And we need to wrap up. I just wanted to briefly point out that Stefan cites our paper with Marcos and Fabian. Not all of them.
Not all of them.
No, because we came up with an idea that has features the same behavior a while back that we call quantum state distillation.
Yeah, exactly.
Where the idea was to get a low entropy state through sort of evaporation for cold atomic systems.
Exactly.
So you let your hot electrons evaporate, and you end up with the mode state inside your optical trap. So and we showed that the entropy actually goes up and goes down. So it's
I think in a way it is very similar.
We were not thinking about the same.
No, I mean, I think in a way it's very similar because basically what you're introducing is this dynamics now with the hot electrons that moves part of your system in a small effective Hilbert space.
All right, we thank Stefan one more time. Thank you for joining us online, and the talk is on YouTube if you want to watch it again. See you next week.